Welcome back to the deep dive. Today, we're getting into something really core to Rust's power. It's memory management.
That's right. We're talking about the stack and the heap and how Rust uses them to get, well, blazing speed and safety.
Exactly. If you've ever wondered how Rust stacks up against C++ on speed but avoids all those memory bugs or what zero-cost abstractions really means.
Then you're in the right place. By the end, you should have a really good handle on why Rust's approach is, frankly, quite revolutionary.
It kind of tackles that old problem, doesn't it? Speed versus safety, pick one.
It does. See, every program uses memory, mainly these two spots,
Yeah.
the stack and the heap. They work very differently.
Okay, let's break that down. The stack.
hmm
I always think of it like stacking plates. You put one on top, you take one off the top, last in, first out.
Perfect analogy. And it's incredibly fast because of that simplicity. Allocating or freeing memory is basically just moving a single pointer.
Super quick, no searching for space, no fragmentation worries, and cleanup is automatic when a function finishes. Like, boom, done.
Right. The heap, though,
Yeah.
that's more like a big warehouse. You can store stuff anywhere, different sizes. It's very flexible.
But that flexibility comes at a cost, yeah. It sounds slower.
It is slower.
Yeah.
You have to actively find a spot that fits, keep track of it, and crucially, you have to remember to clean it up later.
Okay. And that's where the problems creep in with other languages, isn't it? Memory leaks, crashes. I definitely remember those C debugging nightmares.
Oh, yeah. Forgetting to free memory in C, or C++, leads to leaks, or worse, use after free bugs and crashes. Then you have languages with garbage collection, like Java or Go.
They automate the cleanup, which is nice, but then you get those pauses, right? The infamous stop the world garbage collection freezes.
Exactly. The whole application just stops for a moment while the collector does its thing. Fine for some apps, but terrible for, say, games or high-frequency trading. Rust avoids both of these major pitfalls.
So how does Rust manage that? What's the secret sauce?
Well, first, Rust defaults to putting a lot of data on the stack. Things like integers, booleans, small structures. They automatically go onto that fast, simple stack.
Okay, so fast by default for common stuff. What about data that needs more flexibility or needs to live longer? The heap stuff?
That's where Rust's ownership system comes in. It's the real genius here. 3 simple rules enforced at compile time.
Right. Each value has one owner, only one owner at a time. And when the owner goes out of scope, the value is dropped, meaning the memory is freed.
Precisely. And because the compiler checks all this before the program runs, there's no runtime overhead for this safety. That's what zero-cost abstraction means.
No performance hit at runtime for the safety checks.
None. For heap data, Rust uses things called smart pointers like box or RC. They manage heap allocation but still follow those strict ownership rules. It's managed heap usage, essentially.
Got it. So stack focus plus ownership.
Yeah,
How does that cash out in performance terms? You mentioned no garbage collection pauses.
that's a huge one. Predictable performance, no sudden freezes, critical for web servers, databases, anything needing consistent low latency.
And the stack usage helps the CPU cache too, doesn't it?
Absolutely. Stack data is usually laid out contiguously in memory. This means the CPU can fetch data much faster because it's likely already in its cache, keeps the CPU hot, and avoids slow trips to main memory.
And we've seen companies really benefit from this. Didn't Discord rewrite a big Go service in Rust?
They did their back-end service for tracking user statuses. They got rid of massive latency spikes caused entirely by Go's garbage collector. Performance became smooth and predictable.
And Dropbox too, right? They cut memory use dramatically.
Yeah, for parts of their file storage system, they saw like a 50% reduction in memory usage by switching components to Rust. It's about getting C-level performance, but with guaranteed memory safety. No buffer overflows, no dangling pointers.
Okay, so for listeners actually writing Rust code, what are the practical takeaways here?
Well, first, think about your data. Can it live on the stack? Prefer fixed-size arrays and smaller structs when possible. It's often faster.
Makes sense. And maybe use profiling tools.
Definitely. Use tools like Perf on Linux or other platform profilers to see where your memory is actually going and where time is spent. Understand your patterns.
And embrace the borrow checker, I guess, even when it feels like you're fighting it.
Yes, that's
Yeah.
crucial. The compiler isn't being difficult just because. It's guiding you towards a safer and often more efficient design. Listening to the compiler often leads to better code structure.
Good point. And finally, maybe look at how the pros do it.
For sure. Study high-performance Rust projects. Look at Tokyo for async stuff, Serde for serialization, Rayan for parallelism. See how they manage memory efficiently.
So wrapping this up, Rust's approach, it really seems to nail that balance.
It does. Defaulting to the stack, eliminating GC pauses, and using compile time ownership checks. It gives you safety and speed, the best of both worlds.
Which is why we're seeing it pop up everywhere: web, systems, even game development. It's not just about being safe, it's about being safe without giving up that raw performance. A really powerful combination.